All right, so let's do another example here. Let's say that we have a voltage source pulsing from 0 to 24 volts, okay, through an inductor and a resistor connected like this. And we've got a 1 kilo ohm resistor and a 10 microhenry inductor. All right, that's going to be my circuit. And what I want to know, let's say that this was my problem. I'm going to call this node Vs, and I'll call this one Vx. I want to know what is Vx at 30 nanoseconds. Okay? And so what this requires is it requires us to determine what's happening at node Vx. Okay? And so if I were to go ahead and solve this problem, I'm interested in a couple of nodes here. I'm interested in this node, and I'm interested in this node. Mainly, I'm interested in the current flowing in the circuit, because if I know the current flowing in the circuit, I can just multiply that by Vx, or sorry, I can just multiply that by 1K, and that'll give me Vx, right? And so that shouldn't be too hard. I know the current flowing in a circuit with that is charging or in energizing. I can just pull this same equation back in, this charging or energizing equation. Sorry, I keep saying charging because the behavior is the same. So I can start with my IL of t, which is this current, right? And I guess the only thing that's important to find here are the time constant and the final current that's going to be flowing. Okay, so the first thing that I can recognize is that the final current, again, when this inductor is eventually just behaving like a short, I'm going to have 24 volts across this resistor. And so 24 volts across 1K, I can just say that IL final is going to be 24 milliamps, right? And my tau is going to be L over R. So it's going to be 10 microhenry divided by 1K. And that's going to come out to 10 nanoseconds, okay? So tau is 10 nanoseconds. So I can go ahead and write this equation here as IL of t in this circuit is equal to 24 milliamps multiplied by 1 minus e to the minus t over 10 nanoseconds. Well, if I want to determine Vx of t, all I have to do is divide by 1K, this entire thing. So I can just say Vx of t, and hopefully that's clear. It's because Ohm's law says that at any time, it doesn't matter the time, V is equal to I times R. So in this case, my Vx of t minus 0 volts is the voltage drop across the 1K, right? That's this voltage drop. So it's just going to be Vx is equal to IL of t multiplied by R, or IL of t is going to be Vx over R, right? So I can just say Vx of t is going to be 24 milliamps times 1K times 1 minus e to the minus t over 10 nanoseconds. And that's just going to give me 24 volts times 1 minus e to the minus t over 10 nanoseconds, okay? And so then in order to determine Vx at 30 nanoseconds, all I got to do is plug 30 nanoseconds in right here. And so let me just do that real quick. I'll throw that in my calculator. 1 minus the answer, multiply by 24. And I get that Vx of 30 nanoseconds is equal to 22.8 volts. All right, and let me just go ahead and move this down and kind of explain intuitively what just happened, just in case it's not clear. My time constant is 10 nanoseconds, so I know that pretty much everything interesting is going to happen between 10 and 50 nanoseconds. I know that my Vs my Vs is just going from 0 to 24 volts at time t equals 0, right? And then my Vx, what happens to my Vx? Well, initially, no current can flow in the circuit. And so if I don't want any current flowing in the circuit, I have to have a 0 voltage drop across my resistor, because that's really what determines how much current flows. So Vx has to stay right at 0 to start. And then as this current starts building up exponentially, what's going to happen is Vx is going to start building up exponentially, and we're going to get this behavior that looks just like this, which is exactly what we see from this equation right here. It's basically just the charging equation for an RC circuit. It's just the charging characteristic exponential equation, but in terms of voltage, because we multiplied it by a resistance from the original current that we had, right? And so we determined at 30 nanoseconds that I'm basically almost to my maximum value of 24 volts. Not quite, I'm a little below that. I'm actually at 22.8 volts, which is what we determined. And so hopefully this makes sense. Obviously, if you have any questions, feel free to ask. This has been a couple of pretty good examples for energizing a coil. And in the next video, I will talk about energy storage in an inductor. Once we have energized the coil, what is the energy stored, basically? And then after that, we'll go into de-energizing the coil.